of amazing that we survive the atmosphere that we live in. Having oxygen in our atmosphere is incredibly corrosive, and bless you, and it's because this oxygen is very reactive. And so what happens is, and the reason why oxygen is so reactive is that it can accept single electrons. And it makes a group of molecules called reactive oxygen species. So reactive oxygen species, or ROS, is a group of molecules that result from where oxygen has accepted single electrons. So this is the one example where we've taken oxygen and accepted one electron. Partially reduced oxygen is hydrogen peroxide. The hydroxyl radical is the most important one. We're going to focus on this one. The hydroxyl radical will result from the hydrogen peroxide oxidizing our metal ions, and then it will reduce the hydrogen peroxide to hydroxide and hydroxyl radical. This hydroxyl radical is really what we need to be worried about, and we're going to talk more about that. But what we have is two ways in which we can protect ourselves. We have small molecules, antioxidants, and we have enzyme systems. So there's two ways, let me say that again, there's two ways that we protect ourselves against these reactive oxygen species. Small molecules and enzyme systems. And bad stuff happens when those enzyme systems get messed up. It's 100 diseases linked to these failed systems. How do we get these single electrons? This is so weird. Electrons leaking out of the electron transfer chain. They just kind of squeeze out. I find that strange. What we know is free radicals from UV light or radiation, X-rays. A lot of the skin products will put antioxidants in them so that they will accept the radiation instead of your skin. And so what we're going to see is what are those reactions we're going to try to stop. So here's our superoxide radical. Normally, okay, so let's back up for a second. This is the Lewis dot structure for oxygen. You would think that it has a double bond, but in fact it doesn't. Remember when you, some of you may have covered or not covered it in General Chemistry 1, where they show that through molecular orbitals, that oxygen actually only has one bond, not the two, and that it has unpaired electrons. No, it's single bonded, and it's because of molecular orbital theory. So you need the molecular orbital theory. So our Lewis dot structure is kind of weird. So go back and take a look at molecular orbital theory to explain the actual structure of oxygen. And because of that molecular orbital theory, it can really accept that one single electron and become a radical. It's not a free radical, but it's more reactive than the hydroxyl radical. I'm going to focus on this hydroxyl radical. So there's a little bit more information on the slides than I really need. I'm going to focus on this guy because it's really what we're worried about. Now, what is super cool is, these radicals are very destructive. They're bullets. I want you to think of them as bullets. But we can actually use these bullets to our benefit. Macrophages and neutrophils actually shoot out these bullets to kill invading species, invading microorganisms, or to chew up stuff they want to get rid of. So that's kind of cool. Macrophages and neutrophils, they'll use these to their benefit. All right, so this is what's going to happen. I'm just showing you it as an example. So here we have a fatty acid, perhaps a fatty acid that is in that's part of a phospholipid in your membrane, in a cell membrane, right? So you have the hydroxyl radical. That's a result from leaking electrons or whatever, radiation. What it's going to do is that hydroxyl radical is going to pass the radical to a carbon next to a non-saturation point. And then oxygen is going to come around, and we're going to make like almost like a peroxide radical. What happens is it's a chain reaction. It comes, the L stands for lipid. Another lipid comes along, takes the radical, and here we get the peroxide. This peroxide then goes back to a radical by oxidizing our iron, and then it cleaves our fatty acid here and produces an aldehyde at the end. And then another radical. So you get cleavage, another radical. This other lipid gets that radical. So here we've taken one radical and made two radicals. That's really, what I want you to remember from this is that you have a radical from the hydroxyl radical, goes on to the lipid. That radical causes the cleavage of that lipid and is passed on, the radical is passed on to another lipid. So the radical from the hydroxyl radical gets put onto one lipid, ends up cleaving it, and passed on to another lipid. So it keeps going, doesn't stop. One electron can keep going and going and going and going, tearing apart our fatty acid chains. You want me to say that again? Sure. The hydroxyl radical passes the radical to a lipid. It ends up cleaving that lipid. The radical, a result of reactions from that radical, ends up cleaving that lipid. And the radical is passed on to other lipids. I don't need you to know a lot of the details here. Just know that bad stuff happens. Now, having a transition metal around, which we normally do, does also cause further degradation. Now, we end up putting it as a preservative in a lot of our foods and a lot of our things with proteins or lipids in them. We put EDTA, which sequesters or chelates metal ions. So this is why, if you put EDTA, you're not going to have this go on. So put EDTA on your skin. No, I'm joking. So that's a chain reaction. So how do we stop this from happening? How do we stop this to happen? We have enzyme systems. 3 in particular: superoxide dismutase, glutathione peroxidase, and catalase. Now, because it's the end of the semester, I'm not going to ask too much about these, but I do want you to know these, okay? Enzyme systems. Now, there's 2 isozymes for the superoxide dismutase. You have one that contains copper and zinc in the cytoplasm and manganese in the matrix. You have a mutation in the gene so that the superoxide dismutase doesn't work. You get Lou Gehrig's disease, ALS. So it's the gene coding for the one in the cytoplasm. So it catalyzes the destruction of our superoxide radical. Glutathione peroxidase, it becomes oxidized rather than, it takes that superoxide radical, it takes this and it reduces it to an alcohol rather than having it be cleaved here. So remember, sulfur-sulfur bond is an oxidation, so this becomes reduced. So it sort of takes this peroxide and reduces it. Catalase, remember my elephant toothpaste? It will destroy hydrogen peroxide. And these are just pretty pictures of the structures of these. I don't need you to know anything about them except that the glutathione peroxidase has that sulfur that becomes the sulfur-sulfur bond is an oxidized form. Again, bad things happen if we don't have these enzyme systems in place. So I said we had enzyme systems. We also have small molecules. Antioxidant molecules, again, green leafy vegetables, vegetable oils, whole grains, good diet, gives you a lot of antioxidants. Alpha-tocopherol, or vitamin E, which we already saw. This is vitamin E, or alpha-tocopherol. It it can pick up that radical, take it away from the molecule. And the reason why it can pick it up is because that radical is resonance stabilized. It's stabilized. So the radical is going to go to a place where it's more stable. So it can take it away from our lipid and stop that chain reaction from happening. That's why you'll see a lot of the lotions that you put on have vitamin E in them. What happens, this is a lipid soluble. So this can't get out of your body. This is staying there. So we're going to see later, how do we get it out? Beta carotene is, remember, our vitamin A. And that is over here. Beta carotene. It's also got these conjugated double bonds. And remember, the conjugated double bonds absorb radiation. Okay, when you have delocalized electrons, it absorbs radiation. So that's why beta carotene is colored, carrot, right? So what happens when our alpha tocopherol or our vitamin E is going to stabilize that? But remember, this is going to be lipid soluble. So where is it going to go? Well, luckily, vitamin C, which is water soluble, will pick up that radical from our vitamin E and then can be excreted out. So I want you to know that vitamin E or alpha tocopherol will resonance stabilize right here our radical, but because it's lipid soluble, can't be excreted, so it passes the radical onto vitamin C that can be excreted. That I think is pretty cool. So our enzyme systems and our small molecules. The radical is stabilized in vitamin E. We've said that before, but it's lipid soluble. So vitamin C can pick up that radical, stabilize it within its ring system, and be excreted because it's water soluble. Yeah, you get rid of it. So it's very important to have your antioxidants.
So the vitamin E is lipid soluble?
Yeah, vitamin E is one of our lipid soluble.
Oh, right, yeah.
Yeah, so even our vitamin E and our beta carotene, those are both lipid soluble. So it's nice to have our beta carotene. That's why I told you that floor mate of mine that only ate carrots, she turned orange because of all the beta carotene in fats.
So, you said vitamin E, or vitamin E gives free radical vitamin C. What's vitamin A?
Vitamin A absorbs radiation through the conjugated double bonds.